Okay, so this is the last lecture video and it'll be pretty short. So at the end of the last video, I showed you a regression with two axes, two independent variables, age and education, to explain salary. Okay, so then, and also I asked you to calculate the predicted wage given age and education. And it is pretty simple. Like, you just plug in age and education and estimated values. So the intercept is minus 0.075 and the coefficient of age is minus 0.048, and you plug in 30 for age and beta 2 estimate, and education is 16. Then simple calculation, you get 10.341. So this person is expected to earn $10.341 per hour. Okay. Let me ask you another question. There are two independent variables which are statistically significant. Interpret the result. So, just in case if you do not remember what is statistical significance, this is a result of hypothesis testing based on the hypothesis that the coefficient is 0. If you can reject the null hypothesis that the coefficient of this variable is 0, then we say that variable is statistically significant, right? So then at 5%, education's p-value is 0. So it is statistically significant. But age is 20%, 20.5%. So the p-value of age is not statistically significant. It is not rejected, so it is not statistically rejected. I mean, statistically significant. So the answer is C. And remember, that means, so rejection is good in this case. So you wanted to reject that coefficient is 0. For age is not significant. That means it is basically no different from 0. Basically, all the coefficient, all the estimate, say the coefficient of age is estimated to be minus 0.048. Difference from 0 can be just thought of as a random error. Like, it is basically 0, and the difference can be coming from just a random error. That is always possible, right? So that means age does not help predicting salary. That is what you see. So also, what's interesting here is R-square. If you look at the R-square, it is 10.66%. Let me compare the original. Like, if you only use education, the R-square was 10.59%. But by including another variable, it is 10.65%, about 0.06% increased. That means age does not help. As age does not help explaining the salary. So that is obvious. And another thing you need to think about is the effect of including age on the other variable. So the coefficient of education also changed. So let me compare. So earlier, remember, think about this. Education's coefficient is 743 and standard deviation is 0.45. But after inclusion of age, 741. It was 743, but change it. And standard error 456, slightly different. 4560, and here 4562. So it changed. So including another variable will also affect the existing variable too. So you have to recalculate everything. That is the point. Okay. And finally, this is the last example. There was a very interesting article on The Economist, published in like 2016 April, and it reported ice cream's anti-brain freeze effect. So that means the evidence is like this. So the horizontal axis is mean score on PISA reading scale. So PISA is, I don't know, maybe International Association of Education, something like that. This is standardized test, international level test on reading across countries, horizontal axis, and vertical axis is ice cream consumption by country. So test score by country, ice cream consumption by country. And you have a very strong increasing trend line. It is not straight line, so it is nonlinear regression, but idea is the same. R square is nearly 50%. So ice cream consumption explains your test score a lot. How can this be possible? Of course, so based on this, you can say that ice cream will improve test scores. Is that true? Of course not. Of course not. Ice cream does not improve your test score. So it is a problem in interpretation. We tend to interpret the result as a causal relationship. That is very dangerous. This report was published on April Fool's Day in 2016. So the economist fooled you. It is a wrong interpretation. So it is true that the test score and ice cream consumption has correlation. They have statistical correlation that is strong, but that does not imply any causation. So of course, ice cream does not improve test score and not the other side. So test score does not improve ice cream consumption. So there is another hidden variable. The correct interpretation is like this. The economy, like GDP, for example, GDP, rich country consumes more ice cream and has a higher test score. That is better, more natural, more correct interpretation. So what I want to say here is the correlation. Regression just shows you correlation, some relationship. It does not say what causes what. But so far, I interpret it as if one X causes Y, but that was possible because it is obvious in the context, right? Production causes cost. That is obvious, but that is not statistical. That interpretation is economic interpretation, not statistical interpretation. So, like this ice cream example, causality interpretation is really dangerous. You should be more careful in doing that. And another example is like this. So as you see, this regression is nonlinear. This method is possible. Just I cannot teach it right now because it's a little more advanced. So next semester, I teach 420, ECO320, which used to be applied econometrics, but its name changed this semester. So it's like econometrics and data analysis, something like that. So anyhow, there I'm going to introduce some kind of nonlinear regression model. But here, I only limited our attention to linear case. So an example is GDP and pollution. So let me show you the example. GDP and pollution are typical example of nonlinear relationship. So when GDP increases first, then pollution increases. But after a certain point, the people care about the environment, then pollution will go down. So the relationship is nonlinear. Let me show you this example. This is a simulated example. I made it by myself. It is not a real data, a simulated data. So data looks like this. So scatter plot looks like this. This is the scatter plot. Scatter plot looks like this. And if you use a straight trend line, it will go like this. So that means it is very much flat. If you look at the result, X variables, p-value is 79%. So this is not significant at all. So coefficient is nearly 0, 0.01. So which is even smaller than the standard error. So p-value is really high, and this X variable is unrelated, right? However, the true line is like this. This is the correct analysis. So what I'm saying here is, even if the regression result is insignificant, statistically insignificant, you should be careful in your conclusion. Look at, like, what I recommend is, at least look at the scatter plot. Try to draw a scatter plot and see if there is any nonlinear relationship or not. That is my final word of caution. Okay, thanks for watching. You have done a lot of work so far, so I hope everyone has a satisfactory result from this course. So if you need help, let me know. Okay, thank you for watching. The last video will be about quiz 12. See you there.